In Section 2 of Chapter 6, we will be discussing enthalpy and calorimetry. Please have your notes and a calculator handy. Before proceeding with the video, please review these AP Chem learning objectives. First, let's discuss enthalpy, or specifically the change in enthalpy, delta H. It is a state function, that is, a property of the system that depends only on its present state, not its past or its future. And at a constant pressure, the change in enthalpy, delta H, is equal to Q. So it's basically equal to heat as long as the pressure is constant. So we can also refer to delta H, or the enthalpy change, as the heat of reaction. For a chemical reaction, the enthalpy change, delta H, would be the enthalpy of the products minus the enthalpy of the reactants. And so for this reason, the value for the enthalpy change, delta H, could be either positive or negative. The enthalpy of the products could be greater than or less than the enthalpy of the reactants. So just like with heat, if your enthalpy change is positive, we're talking about an endothermic reaction, and if it's negative, we're talking about an exothermic reaction. So let's take a look at this sample problem. We have the combustion of propane, and we have an enthalpy change already provided here, negative 2,221 kilojoules per mole. We're going to assume that all the heat comes from the combustion of propane, and we'd like to calculate the enthalpy change, delta H, if 5 grams of propane is burned in excess oxygen at constant pressure. So this enthalpy change is given per mole, but we don't have 1 mole, we have only 5 grams of propane. And so let's figure out how many moles that is, and then we can take a look at the enthalpy change. Converting 5 grams to moles, we find we have 0.113 moles of C3H8 propane. So now let's multiply by the enthalpy change per mole so we can find the enthalpy change for this given sample here that is not quite 1 mole. So we get negative 252 kilojoules when we multiply the moles in our sample by negative 2,221 kilojoules per mole. In sections 3 and 4 of this chapter, we will take a look at where this value comes from, this enthalpy change in kilojoules per mole, and we'll talk about how to calculate it. Next, let's talk about calorimetry. In first year chem, you did a calorimetry experiment where you found the specific heat capacity of an unknown metal, so you should be somewhat familiar with this concept. But calorimetry is the science of measuring heat. We use a calorimeter. They can range from very simple calorimeters, like a coffee cup calorimeter that allows you to do an experiment at constant pressure, to a more advanced calorimeter called a bomb calorimeter that would allow you to do a calorimetry experiment at constant volume. Calorimetry experiments will often involve in their calculations the use of the specific heat capacity or molar heat capacity. So you maybe remember the specific heat capacity is the heat required to raise the temperature of 1 gram of a substance 1 degree Celsius. And instead of the gram, we can talk about the mole, and that would be the molar heat capacity. This simple coffee cup calorimeter would allow you to do a constant pressure calorimetry experiment. This is where we would look at reactions in solution. Inside our calorimeter, we put the reacting substances and then measure the temperature change that results using the thermometer. If you are looking at a calorimetry experiment that involves a chemical reaction, if your 2 reactants are at the same temperature and then they're mixed and the resulting solution gets warmer, you know you have an exothermic reaction taking place. It is warming the solution. So, of course, an endothermic reaction would cool the solution. And remember, since the enthalpy change is going to be equal to our heat at constant pressure, we can use a familiar equation. Q equals mc delta T is what we learned in first year chemistry, and that's the equation that is more commonly used. This is the one that's in your textbook. Instead of C, they use S for specific heat capacity, and they place that first. But M is still for mass, and delta T is still for the change in temperature. So again, this equation that you learned in first year chem, Q equals MC delta T, is the same equation as the one that we have shown here from your textbook. So let's take a look at this constant pressure calorimetry problem. We have 50 milliliters of 0.100 molar silver nitrate and the same of hydrochloric acid. They're mixed, they react in the calorimeter, and we see a temperature increase of up to 23.4 degrees Celsius from 22.60 degrees Celsius. We want to calculate the heat that accompanies this reaction in kilojoules per mole. So heat, Q, but also our enthalpy change, delta H. We're going to assume the combined mass of the solutions is 100 grams because we put 50 milliliters of each together, and we're assuming the density of water here from these solutions. So 100 milliliters is 100 grams, and we're going to use the specific heat capacity for water as well, 4.184. Now we're asked to find the kilojoules per mole for the precipitate that's formed. So we probably should write down the balanced chemical equation, at least the net ionic equation, when we combine together our silver nitrate and our hydrochloric acid. We're told it's a precipitate reaction, so we should probably do double replacement. Here's our molecular equation, and using the solubility rules, the silver chloride is our precipitate, so I'm going to write the net ionic equation. Okay, and here's my net ionic equation. So we have a 1-to-1 ratio for everything in our net ionic equation. So let's take a look at our molarities and our volumes and see if we can come up with our number of moles of our precipitate. When I take the volume in liters and multiply it by the molarity, I get 0.00500 moles. Now this is for each reactant because they both have the same volume and the same molarity. And so in terms of our ions, from silver nitrate I get 1 silver ion, and from hydrochloric acid I get 1 chloride ion. So this number of moles is the moles of silver ion and chloride ion. And because they react in a 1-to-1 ratio to produce 1 mole of silver chloride, it's also the moles of silver chloride. So this takes care of the per mole part of the answer that we're looking for. Well, almost. We want to do a ratio of our kilojoules to our moles to get an answer in kilojoules per mole. But when we're ready with our kilojoules, then we can just divide it by our number of moles. So now let's take a look at the heat part, the kilojoules. Q equals MC delta T. So we have the combined mass of 100 grams, the specific heat capacity for water, and then the delta T of 0.80 degrees Celsius. We get 334.72 joules. Now we would like this in kilojoules, so I'm going to divide by 1,000. And then this is the heat that was absorbed by the solution. There was an increase in temperature, so heat absorbed. What we're talking about heat that's released by the reaction. They should be the same inside a calorimeter, but I'm going to make this sign negative here to reflect the heat that is released by the reaction. And then now I'm ready to do my ratio of kilojoules to moles. So I'm going to take this number and I'm going to divide it by the moles that I calculated previously. And I'll get my final answer. Negative 67.0 kilojoules per mole released through that chemical reaction. And finally, let's talk about constant volume calorimetry. This is where you would have something like a bomb calorimeter shown here, where you could keep the volume constant. The setup is very much the same as the coffee cup calorimeter, where you have something to monitor changes in temperature and a place for the reaction to proceed. So in constant volume calorimetry, there's no change in volume, so no work is done. Work is negative P delta V, and if there is no delta V, no change in volume, then work equals 0. And then the change in energy will equal Q as long as the volume is constant in your calorimetry experiment. So let's say we have a 1.50 gram sample of methane that was burned with excess oxygen in a bomb calorimeter with a heat capacity of 11.3 kilojoules per degree Celsius. And then the temperature increases by 7.3 degrees Celsius. We'd like to calculate the energy of the combustion per gram. So with bomb calorimeters, instead of a specific heat capacity, we have a heat capacity of the calorimeter itself. So that is the amount of heat required to raise the temperature 1 degree Celsius within the calorimeter. So our final answer for this one, we would like energy per gram. In the last example, we had our kilojoules per mole. So because we want this in per gram, we're already set up in terms of the gram part. Now we just need the energy part. And so we're going to look at our other pieces of information here, our heat capacity and our temperature. And you can see that if we take the heat capacity and we multiply it by the temperature increase, the degrees Celsius will cancel and we'll be left with kilojoules, which is a unit for energy. We get 82.49 joules. When we divide it by our mass, because we want the energy of combustion per gram, we get 55 kilojoules per gram. This should have been a kilojoules right here. And because we're talking combustion, combustion reactions always release heat. And we want to make this then a negative 55 kilojoules per gram.